Hello, in this video, we'll be talking about wires, the prime conductors in most circuits, and how real ones actually have characteristics instead of the ideal conductors we're used to seeing in simulators. We'll be talking about these properties, what affects them, and what we can do in real life to minimize them. All right, so the first question you're probably thinking is, why would I do a presentation on wires when they're just conductors for electricity in a circuit? Well, most people would just assume a wire is just a wire, it's just a conductor, but the answer is much more complex. And the wire, much like a resistor or capacitor, is a component in the circuit. The complexity of wire properties can become even more important when you're dealing with higher voltages, currents, and frequencies. The ideal wire, like we see in every circuit or false set, is just a conductor or connection with no characteristics. So it doesn't have inherent resistance, inductance, capacitance, heat, signal delay, or a number of other properties. And you can actually simulate wire characteristics with a SPICE simulator, although simpler simulators either have limited or no options. So, what wire for what? No doubt you have seen many different types of wires in your lifetime, from large power transmission lines to tiny battery connectors and USB cables. You probably already know that you can't just use a power transmission line as a USB cable or an HDMI cable to connect a 9-volt battery to a tiny clock. However, I have mentioned opening up a old USB cable, exposing its power and ground wires, tinning them, and then using that as a power source for a breadboard. Typical breadboard friendly wires are usually 22 or 24 gauge with a solid core and often a DuPont connector with a zero point 0.1 inch or 2.54 millimeter pitch connector, either female or male. Jumper wires are usually 24 gauge, they're less flexible. They're cut to a specific length with tinned ends. Either one can work for breadboard. A very common mistake for hobbyists is to just find a wire that's just thin enough to fit into a breadboard and assume it'll all just work. I've even made that mistake myself. Your best and safest option is just buy packs of wires for a breadboard and one of the two configurations I mentioned, actually probably both, and try to cover all your bases, so male to male, female to female, male to female. Here's just a quick graphic showing the different things I was talking about. The ribbon cable that I mentioned, that's usually like 22 gauge. Got your male connectors, female connectors. That's what's actually inside the housing. So when you're looking at the DuPont connectors, you're talking about both the contact and the housing, and then the wires usually tend slip through and then connect it all up here. They're also showing some using header pins, straight angle ones, and some right angle ones as well. So as I previously mentioned, wires are not perfect conductors. They have inherent resistance, which is a factor of their material, the contacts on the connectors, the length, and other factors. A typical breadboard wire might be about 0.01 to zero point 0.1 milliohms, and then maybe another zero point 0.4 milliohms for the contacts. And of course, the breadboard also provides resistance, which might result in as much as a 20 millivolt drop across the circuit as a result. They also have inherent inductance, which opposes change in current, but can also cause distortion, receiving or emitting electromagnetic interference, voltage spikes, etc. Typical breadboard wires inductance, especially at lower frequencies, is probably in the nanohenry range, so barely noticeable. But once you start to increase the frequency, it becomes much more of a problem. Also has inherent capacitance. Remember that a capacitor is two close plates separated by an insulator. In effect, you're also describing wires. When you have wires close together, you get more capacitance, and even if it's extremely small in the picofarad range, this can still result in crosstalk, so wires can interfere with each other, unintended signal filtering, slow signal edges, and resonating with the wire's inductance properties. Wires are often insulated, but keep in mind that insulation is not perfect. You can have current leaks, heat loss, etc. When you get more heat on a wire, it increases the resistance, which can lead to even more heat. And extreme heat uh, cases, that heat will break the wires, melt the insulation, and even catch fire. Also, keep in mind that wires are physical structures. They can be broken, strained, which can cause effects on all the properties we just talked about and additional problems. All right, let's start talking by talking about wire geometry. Starting with the wire's diameter is important as thick and larger area reduces resistance and allows for more current, a lower voltage drop, and usually also lowers inductance. And of course, a thinner wire does the opposite. Cross section refers to the shape, such as round, flat, rectangular, or even PCB traces of each has a skin effect. It also affects cooling, packing density, flexibility, and even has an effect on inductance. The skin effect is that at high frequency, the current tends to crowd to the surface of the wire and the current density decreases at the center. You also have solid core or stranded, each with their own pros and cons. Solid breaks more easily and is less flexible, but is usually cheaper. Stranded, while it's not doesn't break as easily, it frays and it's more flexible. Spacing between the wires is also important as it affects capacitance, magnetic fields, interference, and loop area. Loop area is when you realize that power to ground isn't just a straight path, but a loop between the two, and this loop affects electromagnetic interference, induction, and noise. Twisted pair is a way to keep the power and ground together so that they're both affected about the same by external noise, and their magnetic coupling is averaged out between the two. Another solution is coaxial, which is a center conductor surrounded by shielding to tightly control impedance, inductance, and capacitance. Next, let's talk about wire material. Now, copper is the most common. It offers pretty low resistance, really good flexibility. It's easy to solder, and it has a very good natural conductivity. And both today and historically, it was the most common thing used for wires. You can have a tin variant, which protects against oxidation. I've talked about tinning wires. Um, the tin ends are also very common for breadboard wires. It just makes the ends stiffer so that they fit better. Enameled is when you put a really thin insulator, and it's used for wires for things like magnetic cores. But we also have aluminum that's used for high powered systems. It actually is lighter and cheaper than copper, but it's best for power systems, long distance, when you're dealing with short distances, like a breadboard. Aluminum doesn't really have a benefit. You also got silver because that's the most conductive material, but it's really expensive in comparison, but it's absolutely excellent for high frequency. And when it oxidizes, it doesn't really affect the conductivity much. Then you've got copper clad steel, really strong, actually can be cheaper than copper in some cases. Also good for long distance, really good for large antenna. And then you've got nickel and nichrome, which actually this is when wire resistance is actually desirable. I'm not going to really go into that too much right now. We've already talked about stranded and solid. You know, stranded is many thin wires twisted together. It's very flexible. It's resistant to fatigue, but it can easily fray. Solid, that's better for fixed installations when you're not going to move the wires too much. It can be easier to insert into breadboard though, but it can break easier. Insulation materials, PVC is popular for breadboard wires, but you might also run to silicon, Teflon, polyethylene, and potentially others. We've talked about insulation being rubber, but actually, natural rubber slowly stopped being used with wires starting sometime in the 1950s, although synthetic rubbers are still used for certain kinds of wires in niches. Now, I mentioned gauge is in wires earlier. What does that mean? Well, normally, at least if you're in North America, it means American Wire Gauge, or AWG. It was a standardized system for describing wire diameters and cross-sectional areas around wire. It came about in the mid 19th century because different companies that made wire had completely different standards, and telegraphy and things like that needed standardization. Higher gauge means a thinner wire because the idea is the wire starts out thick and then you shave off excess to make it smaller. Once gauge hits zero, the thicker the wire, it goes into 1/2, 2/0, and such. And it's at that point it's pronounced 1/0, 2/0, etc. But those are really thick wires. Again, you probably will just hear about it in North America, especially the United States, but also in Mexico and some other countries. Elsewhere, you usually just use metric wire sizes, usually expressed in millimeters. The British had standard wire gauge as well, but that's pretty much obsolete. And you used to have to explain that standard wire gauge and American wire gauge were not compatible. Every gauge step changes diameter by about 12.3%. Every three sizes roughly doubles or halves the area, and then every six sizes roughly doubles or halves the diameter. It's a pretty good rule. I have a little equation for determining wire diameter in inches. I don't know it off the top of my head for millimeters, and then also determine area from diameter. Here's just a rough chart I put together of gauge and its size in millimeter and inches. Um, let's see, taking some examples for showing doubling. So 4 to 10, that's 6, and you'll notice in inches that is doubled. Let's see, let's find something else here. I don't think I see a 3 difference to show that, but that would be area anyways. All right, so as you recall from earlier videos, resistance resists the flow of current and dissipates it as heat. More current leads to more heat, and heat affects resistance and conductivity, which can eventually cause component damage and even melting insulation wires, maybe even fires in extreme cases. Thinner or longer means more resistance, thicker or shorter means less resistance. It also causes a voltage drop per Ohm's law. You may see an issue in practice with USB cable suddenly breaking because either the wire is so thin that it breaks or overheating causes it to break since there's so much less area to dissipate the heat. When it comes to low power hobby electronics, that resistance largely means voltage or signal errors, and in some cases that actually may be pretty significant. Keep in mind, though, that the connectors and the breadboards themselves actually provide a lot more resistance than the wire itself. So those tend to be the problem with resistance and conductors versus the wire. This is also why breadboards aren't suited for work when it gets to high current or high frequency. So let's move on to inductance. Now, current flowing through a wire creates a magnetic field. We've already talked about properties of induction in a previous video. When that current changes, the magnetic field resists the change and causes a momentary spike in voltage. Now, a straight wire is about, I would say, 1 to half a microhenry of induction per meter, or 3.28 feet. If you have induction and capacitance, which you're going to have those properties in a wire, it can create an LC system that causes signals to overshoot, unintended oscillations that cause ringing in the signal. If you look on this in an oscilloscope, you might see these oscillations at the beginning and end of each signal. And all of this can actually take time to settle down. It may seem instantaneous to the naked eye, but when it comes to a circuit, every nanosecond matters. Inductance can become an even bigger problem at high frequency as the current is constantly being changed. If that wire is part of a loop, it can cause additional problems, high inductance, stronger magnetic fields, electromagnetic interference issues, because it essentially turns the loop into an antenna. And next we have capacitance. Now in previous videos, I mentioned how a capacitor is basically just two conductors separated by some form of insulation. Two close wires, PCB traces, wire and ground, and wire and shield all cause capacitance. Voltage is resisted initially by capacitance by spiking the current. This is kind of a reverse of the inductance, and high frequency can result in some serious current spikes. You'll get about 20 to 200 picofarads of capacitance per meter, or 3.28 feet of wire. Wires that are closer, induction type, insulation type, I mean, white wire geometry and other factors can all have an effect on the capacitance. And then you have crosstalk. In this case, it's when two close wires can induce current in one another, otherwise interfering with signals that are otherwise isolated. All right. Let's talk about speed and propagation next. Now, in an ideal wire, we have instant speed, no propagation delay, but real world has, a thing we like to call physics. Electrons actually drift pretty slowly, but the changing fields which carry the electricity are moving down the wire at anywhere from 50 to 80% of the speed of light, which is anywhere from 150,000 to 270 kilometers per second. Propagation delay is how long it takes a specific signal to travel a distance. Usually it's measured in nanoseconds or billionths of a second. Signal speed is set by the electromagnetic environment and it can be affected by insulation material, wire length, geometry, and inductive properties, among other things. And a crude example here is a 10 centimeter or 3.9-inch wire delay is about a half a second. But if you make that 1 meter or 3.28 feet, it becomes 5 nanoseconds. You make it 10 meters or 32.8 feet, and that suddenly becomes 50 nanoseconds. And bit by bit, it becomes increasingly more significant. The delay can be a very tight fit in the circuit too, so keep in mind each component may depend on the delay being within a very tight range, often expressed as nanoseconds. Look at any data sheet and you'll notice. When it comes to insulation, for example, PVC has a slower propagation, so you can get more of a delay. Polyethanol is better, while air or spacing can often be the best. If the delay is significant enough, the wire is no longer a wire model, but a transmission line model, which also includes, among other properties, signal reflection. Also, keep in mind with hobby electronics, the breadboards themselves can introduce a lot of problems, delay, variation, signal reflections, noise coupling. Now, I just realized that I've inadvertently introduced another passive component that we've only briefly mentioned in previous videos. That's the transmission line. Well, once a wire has gotten so long that it no longer effectively instantly sends the signal, different points along that wire have become different voltages and currents, and they're no longer uniform. That's when we have a transmission line, which introduce a whole host of other properties and issues. The wire delay itself becomes comparable to a signal rise time. This is very important. You'll notice on data sheets where a signal has to fit within a certain rise time potentially. Even a wire as short as 10 centimeters you could start to see rise times measured in nanoseconds. And even this short a distance can interfere with things like SPI bus signals. If the line also doesn't match the natural impedance of the load, the signal may start to reflect back. This is less of an issue, and your frequency is relatively slow, like you're dealing with milliseconds or microseconds. One solution is to add a thing known as a terminating or terminator resistor, so that the resistor absorbs the signal reflection. You'll see this a lot in real life, actually, without realizing it. Slower edges and shorter wires reduce these effects. Sharper edges, longer wires make them worse. There's also a point where you really want to switch to a PCB as the best solution to not only this, but all the other issues with wires because of the problems inherent with breadboards. But there's some other solutions. You can slow down the clock, add in some series resistors, a terminating resistor, or maybe something like a twisted pair geometry with power and ground wires. Now, here's a little thing I made with transmission lines and Volstead. The actual length on the graphic here that has nothing to do with the actual length it's simulating. You can change the delay, which is going to affect the length, and you can put some impedance in there as well. That's about the extent of it. This one's hooked to a switch with a light switch. Now, if you'll notice, there's actually a bit of a delay and there's some flicker and some other stuff. And this is the kind of thing you might run into with the transmission line. Now, let's move on to talk about ground and return path. Now, a common misconception, especially for beginning hobbyists, is that ground means zero voltage, and actually it doesn't. You may have looked on every circuit when I did Ohm's law, and you're like, okay, when it finally gets to ground, it says 0 volts. Well, that's a simplified simulator and the it actually is taking a path. It's the path. Ground is the path that current takes to return to source. If you'd done every circuit, you did Ohm's law, and you tried something in real life where you just kind of left the ground wire going to somewhere random, thinking that was going to work, it actually doesn't. You'll notice that ground actually has to go back to the source. Now, the current doesn't just choose a random return path or spread out everywhere. With low frequency, it tends to pick the path of least resistance, while at high frequency, it tends to pick the path of least inductance. And keep in mind that wires have both the parasitic resistance and inductance that we've already discussed. That means current returning to source could pick an unexpected or unplanned pathway, potentially leading to issues, including something like short circuiting. Since inductance depends heavily on geometry, long, tightly wound pathways actually might be better than short, wide paths. Shared ground wires can also interfere with other components. Shared connections to breadboard ground definitely have issues that become more apparent with higher frequency or current. Ground planes often exist on PCBs, basically an entire layer devoted to ground to provide low inductance return paths. I've already mentioned the twisted pair solution where you keep power and ground wires together twisted. I mean, obviously each wire is isolated, but they're kept extremely close. You will commonly see this used a lot, such as with Ethernet or USB cables. Just open up a USB cable and you'll see. All right, so I've talked about EMI, electromagnetic interference. Now, most people have heard this probably in pop culture, usually relating to some kind of a weapon or an effect from a nuclear blast. Those things would have insane amounts of EMI. Wires carry signals, but they also radiate and receive electromagnetic energy. Too much energy can fry a circuit, hence why you hear it mentioned as a weapon. I need to emphasize that it does do both. It transmits or emits and receives the signal. So it doesn't do just one or the other. A higher frequency is going to generate more as the and magnetic fields are just constantly changing. This is a big problem with noisy switching power supplies, something we'll probably talk about in a later video. In fact, this is one of its biggest weaknesses. Large loops will radiate more and also receive more. Small loops will reject noise better and radiate less. Inductive coupling is why you get things like transformer-induced audio hum, relay coils causing problems, and motors affecting nearby sensors. In common hop electronics, your biggest sources will be motors, relays, solenoids, switching power supplies, and fast digital signals. Now, some of the same solutions also help with EMI, and I've previously mentioned things like twisted pairs, loops, and shielding. All right, so let's return to Ohm's law and some stuff we covered in earlier videos and see how all of this new information might affect things. Now, a reminder is Ohm's law is that voltage equals current times resistance. We can now factor in the wire characteristics to be incorporated into that formula. So if we had 50 milliamps and 100 ohms, we'd get 5 volts. Now we can add 21 milliohms to that equation and we'll still get roughly 5 volts, but it'll actually be 5.00105 volts. Keep in mind we're not bringing in other factors like connectors and the breadboard, etc., which actually will put in a lot more resistance. If we actually want to calculate the wire's resistance, it would be equal to P, which is the material's resistive properties. L is the length, and A is the cross-sectional area. So with a 1 meter copper wire, we'd see about 21 milliohms, which is what I used in the revised equation. If we want to check the wire's inductance, the formula would be that the voltage equals inductance in henries times current in amps divided by time in seconds. You should look at the actual equations on the slide too. Um, Simply put, 1 Henry produces 1 volt when the current change is 1 amp per second. We can also check the current with current equals capacitance times voltage in volts and time in seconds. Keep in mind when these wires become transmission lines, we also have characteristic impedance. Impedance equals the square root of inductance in henries divided by the capacitance in farads. Now, this can lead to some ideas for best practices when you're actually making real life circuits. First, keep your wires short. They shouldn't be unnecessarily long, especially when you're dealing with faster signals like clocks, SPI, analog sensors. Keep the signal and ground wires together in a twisted pair, although obviously they're going to be insulated from each other because you don't want a short circuit. Um, like with a breadboard, if you have a power source connected only one rail and you want to connect the other rail, make sure the power and ground are next to each other, not on opposite ends of the rails. For example, if wires are sensitive or noisy, then take the opposite device, distance them from other wires. This includes wires like operating motors, relays, and anything from switching power supply. Decoupling capacitors between power and ground pins with an IC. It might seem a little awkward sometimes, but it can help in high frequency operations. If possible, switch to PCBs for serious circuiting, but obviously PCBs are their own category, harder to deal with and more expensive. I'm not even right now up to the point of being able to design my own PCBs. Grounding planes, star groundings, there's some great ways to handle grounds. Series resistors on fast digital lines slows the edge, reduces ringing, and lowers EMI, which is basically just a small resistor between whatever wire you have coming from, say, a microcontroller to an SPI device. So don't make a direct connection, have some path where they have to go through a resistor. I also can't emphasize this enough. Use flyback diodes with inductive loads. Don't risk a certain undesired flyback voltage. Lastly, get yourself an oscilloscope. This lets you diagnose issues and see what happens when you better your practices. Okay, we've done a lot of talking about wires, so let's wrap this up. An ideal wire is a perfect conductor with no characteristics, but that's not how real world wires work. They're not ideal wires. Wire characteristics can be simulated with SPICE, but generally not with the other simulators, although there is some support for a basic transmission line in Falstad. Different wires have different characteristics for different jobs. 22 to 28 gauge solid core or stranded copper wire insulated with PVC is the most common you'll see for breadboard work. You often have to just see tinted ends in some cases with various connectors. Jumper wires are more inflexible and they're usually cut to specific lengths and their ends are just generally tinted. Real wires have properties, resistance, capacitance, induction, that could all be compounded by wire geometry, use of breadboards, wire length, etc. They can both interfere with and be interfered with by other components. The more complex and higher frequency a circuit become, the more these things become a problem. There are plenty of solutions, but eventually you might want to think about moving to printed circuit boards. Breadboards are nevertheless good enough for low frequency and low current work, but you'll eventually run into their limitations. Well, until next time, have a good one.